Welcome to Fun Facts Online. When we picture a glacier melting, we usually imagine the sun beating down from above, or warm air turning ice into streams of water. We see the dramatic images of massive ice chunks calving off into the sea with a thunderous roar. But what if I told you the most destructive force, the one accelerating this melt at an alarming rate, is completely invisible? Deep beneath the serene surface of the world's fjords, a silent war is being waged. Powerful, skyscraper-sized underwater waves are relentlessly battering the submerged faces of glaciers, eating them away from below. This is the hidden story of how our oceans are melting glaciers from the inside out, and it's a critical piece of the climate puzzle we're only now beginning to understand. Today, we're diving deep into the unseen world of these internal waves, exploring how they're born, how they create a devastating feedback loop of destruction, and what their cascading consequences mean for all of us. Let's get started. First, let's set the stage. Glaciers are vast rivers of ice flowing under their own immense weight. Where they meet the sea, they carve out long, deep, narrow inlets called fjords. For decades, we thought rising air temperatures and warming surface waters were the main villains in the story of glacial retreat. But scientists now realize that a huge portion of the melting happens out of sight, deep underwater. This interaction is far more complex than ice simply melting in warm water. It's a symphony of powerful forces, and the lead conductors are underwater waves. So what are these hidden architects of demise? The ocean isn't a uniform bathtub of water. It's layered or stratified. You have layers of different temperatures and saltiness, and therefore different densities. Think of oil and vinegar in a salad dressing. The interface between these layers can support waves, just like the surface of the ocean. These are called internal waves. And in the confined, deep environment of a fjord, they can become behemoths, sometimes reaching the height of a skyscraper. These internal waves are so effective because they act like massive delivery trucks, transporting huge amounts of heat from the deeper, warmer parts of the ocean directly to the submerged face of the glacier. This is far more efficient than simple heat diffusion. They also create intense turbulence, which violently mixes the water. This breaks down the thin, insulating layer of cold, fresh meltwater that would normally protect the glacier from the warmer, saltier seawater around it. It's like constantly stripping a protective blanket off the ice, exposing it to the full warmth of the ocean. So where do these powerful waves come from? They have three main origins. The first and most dramatic source is calving. When a house-sized or even stadium-sized iceberg breaks off and crashes into the fjord, it creates a surface tsunami, the kind we see in documentaries. But the energy from that violent impact penetrates deep into the water column, generating powerful internal waves that can slosh back and forth for hours, long after the surface is calm again. In the most extreme cases, these aren't just waves. They're more accurately described as internal tsunamis. Direct observations in Antarctica have confirmed these internal tsunamis drive vigorous, deep mixing, a process whose importance was previously underestimated. This isn't a localized freak event. It's happening wherever glaciers calve into the ocean, from Greenland to Patagonia. The second major driver is the rhythmic pulse of the tides. As the tide flows in and out of a fjord, it forces the stratified water over the irregular seabed. Many fjords have underwater ridges called sills, often piles of rock and debris left behind by the glacier when it was larger. When the tidal flow passes over a sill, it disturbs the density layers, creating a continuous train of internal waves that radiate through the fjord. This provides a constant, steady source of mixing energy, a non-stop assault on the glacier face. The third, and increasingly recognized, source is subglacial discharge. This is the meltwater from the glacier's surface that drains down through cracks and tunnels to the very base of the glacier. It then emerges into the fjord as a buoyant plume of fresh water, shooting upwards from the seafloor. These rising plumes are incredibly turbulent, and, as they ascend, they interact with the stratified fjord water, emitting high-frequency internal waves. These waves then travel along the glacier's underwater face, promoting melting far from the original plume. In fact, when scientists included the energy from these specific waves in their models, the predicted melt rates increased by as much as 70%. Now here's where it gets truly concerning. These processes don't just happen in isolation. They feed into each other, creating a powerful and dangerous feedback loop known as the calving multiplier effect. It's a vicious cycle of melt that rapidly accelerates a glacier's retreat. Let me walk you through it, step by step. Step 1. Warm ocean water transported to the glacier by fjord circulation and these internal waves starts melting the submerged part of the ice. This is especially effective at the very base, where the warmest, saltiest water usually sits. Step 2. This melting carves out an undercut, essentially a cave or notch at the waterline or base of the glacier. Step 3. This undercut removes the physical support for the massive weight of the ice above it. This creates immense stress and makes the glacier's edge, or terminus, incredibly unstable. Step 4. The increased stress leads to more calving. A massive chunk of ice breaks away. Step 5. As we just learned, this huge calving event generates more powerful internal waves and internal tsunamis. Step 6. These new powerful waves mix the fjord water even more vigorously, stripping away any protective cold layers and bringing even more warm, deep ocean water into direct contact with the newly exposed ice face. Step 7. This enhanced contact with warm water leads to accelerated melting, which carves an even larger undercut, and the cycle repeats, each time with more intensity. Modeling studies suggest this multiplier effect can lead to calving rates up to 10 times the average melt rate. It shows how even a small increase in ocean temperature can be amplified by these dynamics into a much more rapid and catastrophic glacial retreat. While these fundamental processes are happening globally, the way they play out varies in different regions. In Greenland, for instance, the fjords are deep and directly influenced by warm waters from the North Atlantic. The massive amount of surface melt on the ice sheet also means that subglacial discharge is a particularly important driver of internal waves there. Greenland is a key research site for studying this calving multiplier effect. In Antarctica, the situation is a bit different. Many glaciers there terminate in enormous floating ice shelves. But where they do end in fjords, like on the Antarctic Peninsula, calving-generated internal tsunamis are a hugely significant driver of mixing, perhaps even more so than wind and tides. And in Patagonia, glaciers exist in a warmer, wetter climate. Many end in freshwater lakes instead of saltwater fjords, which changes the dynamics. But where they do meet the ocean, a unique combination of shallow sills, strong winds, and heavy freshwater input creates its own complex set of conditions that scientists are actively studying. This isn't just an abstract scientific problem. The accelerated melting and the churning of fjord waters have profound, cascading consequences for ecosystems and for human societies. Fjord ecosystems are finely tuned to the conditions created by glaciers. Change those conditions, and you trigger a ripple effect through the entire food web. For example, the upwelling driven by subglacial discharge plumes can act as a nutrient pump, bringing nutrient-rich deep water to the surface. This can fuel massive phytoplankton blooms, creating feeding hotspots for fish, seabirds, and seals. However, this effect is a double-edged sword. In other cases, the meltwater is so full of sediment that it makes the water turbid, blocking sunlight and shutting down photosynthesis, which crashes primary productivity. The entire food web can be restructured. There's also the issue of contamination. As glaciers melt, they release decades or even centuries worth of trapped pollutants back into the environment. This includes heavy metals like mercury, which can build up in the food chain, reaching dangerous concentrations in top predators like seals and polar bears, and in the fish that local communities depend on. And for the communities living along these coasts, especially in places like Greenland, these changes are an immediate threat to their livelihoods and culture. Fisheries, a cornerstone of the economy and subsistence, are at risk as fish stocks decline or move. The hunting of marine mammals, central to many indigenous cultures, is threatened by the changing ecosystem. And from a safety perspective, increased calving means more frequent and larger tsunamis, posing a direct threat to coastal towns and infrastructure. Given these immense stakes, scientists are racing to better understand and predict these hidden dynamics. The problem is that the processes involved span a vast range of scales, from the millimeter-thin layer of water at the ice face to the kilometer-wide circulation of an entire fjord. Our current global climate models don't have the resolution to see these details, so they have to use simplified estimates. Researchers are working hard to improve these models, but to do that they need better data, and they're getting it with some amazing technology. They're laying fiber optic cables on the fjord floor to provide continuous, high-resolution measurements of temperature, essentially listening to the sounds of calving and the resulting internal waves. They're also deploying autonomous underwater vehicles, or AUVs, robotic submarines, to venture into the dangerous and previously inaccessible zone right at the glacier's edge. This research is crucial. The story of these silent, powerful underwater waves is a stark reminder that the greatest threats are not always the most visible ones. They are a critical component of the engine of global sea level rise, with direct consequences for coastal communities everywhere. The fate of our coastlines, the health of polar ecosystems, and the future of Arctic communities may very well depend on our ability to finally understand the immense power of these unseen underwater waves.